In this video, I'll be talking about electric field due to an infinitely long charged wire. So let us consider you have a very long, infinitely long charged wire. Okay, and we are interested in finding out the electric field at this point P. Let's say this point P. And we assume this to be infinitely long. And if you look at any point, the electric field, the direction of the electric field is always perpendicular to the surface or perpendicular to the line. So at each point, the electric field is perpendicular, is in both direction. So the electric field direction is always perpendicular to the surface. Okay. And in this direction too. So the reason we choose this to be infinitely long is because if this is at the edges, at this edge, there are some fringe field. That means the electric field could be in this direction. From this point, it could be in this direction. It could come this way. So these fields are called the fringe fields. Okay. And at this point P, this could add up some of the electric fields. But now if it is infinitely long, then the contribution of the electric field at this point P due to the fringe field or due to these fields are very, very minimal. That's the reason, that's the only reason we choose this to be infinitely long or very, very long wire. Okay. Now how are we going to solve this problem? Okay, or how are we going to calculate the electric field at this point P using the Gauss law? So what we're going to do, we're going to again choose a Gaussian surface here. Let me erase all these things. Okay, I will erase this one. And this is positively charged. So in order to make life easier, we're going to choose a Gaussian surface which is cylindrically symmetric. Okay, so the choice of choosing a Gaussian surface is entirely upon you. You can choose any surface, but just to make life easier or just to make the integration possible, we choose a Gaussian surface such that we can perform the integration so easily. So in this case, we're going to choose the Gaussian surface to be a cylinder, just like this. Oh. Okay, so just like this, and let's assume the distance, this distance is r. This is r, the distance. Now we're going to find out the direction. As I mentioned earlier, this is a positively charged cylinder. So the electric field direction, if I just took at any point on the cylinder, the electric field is always radially outward. It doesn't matter where you choose, the electric field is always radially outward. Okay, at all points the electric field is outward. Now what is the direction of the area vector? The area vector, if I just choose any location at this point, the area vector is also in this direction. This is the area vector. If I choose at this point, the area vector is this way. This gives the direction of the area vector. Okay, this is the direction of the area vector. But now if I look at how about this end? This is also part of the Gaussian surface. How about this end? if I look at this end, the electric field at any point at this point is in this direction, but the area vector, this is the direction of the electric field and this is the direction of the area vector. This is the direction of the area vector. Now over this area, over this circle, the electric field and the area vector are perpendicular. Area vector and electric field are mutually perpendicular. What does this mean? That means the angle theta between area and the angle between area vector and the electric field is 90 degree. So cosine 90 is 0. So the flux passing through these two closed surface is exactly the 0. So there is no flux passing through this area. And this is also one reason. Now if you choose it, if it is not infinitely long, then there will be some flux passing through this area, and then calculation will be a little more complicated. That's the reason we choose infinitely long, so that there is no any fringe field passing through the closed surfaces or through this the circular ends. Okay, now let's apply the Gauss law. Okay, so what does the Gauss law tell you? The Gauss law tells you the total electric field or the total electric flux passing through a closed surface is equal to Q enclosed divided by epsilon naught. Okay, and I should also mention one thing. We assume here the lambda is the line charge density. Line charge density. What does the line charge density means? That means the charge per unit length. Per unit length. That means how much charge you have in a unit length gives you the line charge density. Okay. And we assume the length of the Gaussian surface, the length of this Gaussian surface is L. That's the length. Okay. So as we know, this is the lambda charge. The lambda is the line charge density. So the total charge enclosed by this Gaussian surface will be the total charge enclosed, Q enclosed, would be simply equal to the lambda times L, because the lambda is the line charge per unit length. Sorry, lambda is the charge per unit length. If you multiply by the length, that gives you the total charge enclosed by that surface. Okay, this is how much the charge is enclosed by the Gaussian surface. Okay, now let's go back to this equation. At each point, again, at each point over this area, the electric field and area vector are parallel, and the electric field is constant at each point. So E is constant just by symmetry. As it's infinitely long, the electric field at each point is constant. It's not changing. Okay, so I can take E out, and then we have dA vector, dA, and this one would be, what is that Q enclosed? The Q enclosed is equal to lambda times L divided by epsilon naught. Lambda times L divided by epsilon naught. Okay. So E and this gives you the total surface area of the Gaussian cylinder. And again, remember, as there is no flux passing through this end, we're not going to take the area of this end. We're going to take the area of only this portion. So how do you find out the area of the cylinder? The total area of the cylinder would be 2 pi r times L. That's this area is the area of the cylinder without including the circular ends. Okay, and now this is equal to lambda times L over epsilon naught. This L and this L cancels out, so what we're left with now is E is equal to lambda over 2 pi r epsilon naught. This is the, sorry, my bad, it's lambda. It should be lambda over 2 pi r epsilon naught. This is the formula for calculating the electric field due to a line charge, infinitely long line charge. It can also be simplified this way. Now let's multiply 2 on the numerator and the denominator. So this one will be 4 pi epsilon naught times r, and E can be given as k 2k lambda over r. Lambda over r. So this at 2k lambda over epsilon naught. So this is the another formula for calculating the electric field due to a long line charge density. What's the k here? K is a okay, I think my bad. It should be r here. This is r, 2k lambda over r. And what's the k there? The k is is 1 over 4 pi epsilon naught, and this value is 9 times, as you know that the value of k is 9 times 10 to the 9. I think my pen is dying out, so it's 10 to the 9 Newton meter square per coulomb square. Okay, so this is the formula for calculating the electric field due to a long line charge. If you need to take all the text here, so I have included all the text here. Okay, so you can go, all the details here is included here, and that's the final formula for calculating the electric field due to a long line charge density. And now what's the important point about this one is, if you have a long line charge density, then the electric field varies as 1 over r. If you have a point charge, then the point charge varies as 1 over r squared, and that's how the variation of the electric field is due to a